Okay, we'll get started today with what we're going to work on. First things first, obviously we just finished the exam. The results should be available for you now. Let me know if any of you have trouble seeing them now in Blackboard. You'll go through your grade book and click on the score, and that should take you to the questions and answers that you had. The exam this time was a bit of a bloodbath, so here's the statistics. So our first exam, to remind ourselves, was an average about 13.5. This one was almost 2 points lower. That's a fairly normal trend now because that was pretty much the exact same thing that happened last year. So you're really no statistical difference between your average and last year's average. So the only thing I'll say about this is that. But sorry, wait just a second.
I lost my adapter for my Mac.
Okay, all right. So we're gonna. So those are just a quick rundown of the exam stats. Keep in mind that the book is not closed on anybody because we've only gotten 40% of the exam scores. 40% of the points right now. We have 54 more to go with the third midterm and the final. So we have kind of a sprint to the finish coming up. So if you're happy where you are right now, don't rest on your laurels. If you're not happy where you are right now, there's still plenty of opportunity to turn things around, but like I said, after the first exam, that requires you to adjust your habits and to figure some things out as we go into the final stretch here. And as always, I'm happy to talk to any of you about the results from this exam or things that you can do moving forward to help you out on future exams. All right, so with that, let's get into today's material, which is going to beginning Chapter 8. We are a little bit ahead of the syllabus right now, but that's okay because then you'll be hopefully more prepared for the homework assignments, and it'll give us a couple days at the end to review some things before the final exam. So what we're going to talk about in the last two chapters, believe it or not, we're coming up on the last two now, are the states of matter, solid, liquid, and gas. So this chapter, Chapter 8, is all about gases, and then we'll talk about solids and liquids starting in the next chapter, Chapter 9. So we should have some idea from our very basic science courses what the differences are between solids, liquids, and gases. So let's just quickly review that. Solids have a fixed volume and shape. All right, now obviously you can mold them in different shapes, but once they have a defined shape, they stay that shape, they don't flow at all. And then liquids and gases are what we call the fluid states, the ones that are able to flow freely. So liquids have a fixed volume. So the volume of a liquid is constant, but the shape of the liquid conforms to whatever container it's in. And then another way to state this is that a liquid has an upper surface. So even though the molecules or the atoms in a liquid are able to move around freely, and even though it flows, they're not flying off in all directions. There is some upper surface that bounds them together, keeps them in a fixed volume. Now gases, the first ones we're going to talk about in any detail, these are ones where the atoms or molecules are moving around completely freely, and so the gas is going to completely fill the volume of the container that it's in. All right, so even if I took a little bit of gas and, like let's say I popped a balloon at the front of this classroom, those gas molecules that were in that balloon are going to now spread all the way around the room. They're not going to be bound in any specific location. They're going to completely fill the volume that's available to them. Gases are freely flowing. And compared to the other states of matter, they have low density. All right, so remember density we introduced way at the beginning is the mass per unit volume. And for gases, those tend to be very small, usually several orders of magnitude smaller than a typical liquid or a solid. All right, so that's sort of the basic properties of solids, liquids, and gases. We'll come back to solids and liquids in Chapter 9, but this chapter is all about gases. And the first property of gases we need to understand is what's called pressure. We talked a little bit about pressure in Chapter 7 when we were dealing with expansion work. And so remember that pressure is force divided by area. So whenever you have a gas, either in a closed system specifically, the gas is going to be exerting some force on the container that what's ever bounding it, and then dividing the force by the area is going to give you what's called pressure. So the first thing we're going to talk about are how to measure pressure and what the common units are. So if you want to measure atmospheric pressure, so the air that surrounds us has some pressure associated with it, and you've probably heard of people on the news, the weather on the news talking about the barometric pressure. So a barometer is a device that's used to measure the atmospheric pressure. So typical, the old school barometers were just made out of a column of mercury. So mercury is a dense liquid. You would make a column of it, and then essentially the air pressure that pushes down on the outside of this is going to force mercury up into the column. Okay, so the air pressure is pushing down, that forces the mercury up, and you measure the height of that column as a way of getting the atmospheric pressure. So the atmospheric pressure is around 760 millimeters of mercury. All right, and it turns out the math works out that it doesn't matter how wide your mercury column is, the height is going to be the same, and it's typically about 760 millimeters at at normal pressure conditions like we are here. So that corresponds to about 2 feet or so. 760 millimeters is right around 2 feet, I think. 30 inches, so maybe a little bit bigger than that. Now, if we were to use water instead, so the question is, why do we use mercury for a barometer? Why don't we just use something like water, which is a lot more commonly available and not going to poison us if we accidentally drink it? Well, the difficulty is that for water, because it has a lower density, atmospheric pressure is about 34 feet. So sure, we can make a water barometer, but it would have to be 3 stories tall, so that's not very practical. So that's why we use mercury in barometers and in many pressure measuring devices. And so the key point is that a barometer is used to measure atmospheric pressure. So if we're giving you a problem that says the barometric pressure was whatever, 760 millimeters or something around there, that means it's the pressure of the atmosphere that's surrounding you. So for chemistry experiments, though, what we often do is measure the pressure of a sample of gas. So we're not going to measure just the pressure that's surrounding us, but we're going to have some closed system, some chemical reaction happening that we want to measure the pressure of. And so for that, we use what's called a manometer, which is what is used to measure the pressure of a gas sample. Now these pictures are probably kind of small on the screen, but if you have the notes in front of you, you might be able to see a little bit what's going on here. So there are 2 types of manometers that we can have, and one is a closed-end manometer. So essentially we have this sort of S-shaped tube here. The gas is in here in this bulb. It's pushing down on the mercury, and then it's going to move the mercury up or down, up this tube depending on the pressure that's against it. And at the other end here, it's completely closed off, and so on the other side of the mercury column is a total vacuum, no pressure at all. So this is called closed end, and the pressure is measured relative to vacuum. So if you want to get the pressure of the gas in this, you just have to measure the height of the column. So if there's no gas in here, the 2 mercury columns, the 2 sides of the U will be exactly at the same height. And then if the gas pressure is pushing down, it's going to cause this one to go a little bit higher because of the imbalance in pressure. And so that difference in height is going to give you directly the pressure of the gas. So that's shown in the figure on the right here, where if you have gas in there, the one side of the tube is a little bit lower than the other because of the pressure from the gas, and this difference in height directly gives you the pressure of the gas in millimeters of mercury. The other way to do it is what's called an open-end manometer, and so for this, as the name implies, one end of the manometer is completely open to the atmosphere. So on this side you have atmospheric pressure pushing down, and so because of that you're measuring the pressure relative to the atmospheric pressure. So in order to use an open-end manometer, you need to also know what the atmospheric pressure is, because the pressure of the gas in the bulb here, this gas pressure is going to be the atmospheric pressure plus and minus the difference in height between the 2 sides. So the one on the left here shows a situation where atmospheric pressure is higher, so this side is pushing down harder and your column is higher on this side. So this pressure would be different from atmospheric pressure by that delta H value, but lower than atmospheric pressure. And then on this side, if the pressure of the gas is higher, it's pushing down stronger on this side than it is on this side. So the mercury column is lower here, and the delta H is going to be a difference in pressure where the pressure of the gas is higher than atmospheric pressure. So there's two different ways of measuring pressure. You might see a little bit of that on the homework, but in general, it's not going to be a big deal moving forward. Now, when we measure pressure, as I said, we can do it in millimeters of mercury. We can use that as a unit of pressure, but there's some more convenient ones or more common ones that we're often going to use as well. The SI unit for pressure is called the Pascal. So remember, SI are those standard system of units that you're going to use these mostly in physics courses. We don't always use them in chemistry. So 1 Pascal is 1 Newton per meter squared. So remember that pressure is force per area. So a Pascal is 1 Newton of force distributed over an area of 1 square meter. So this is something you'll see in physics if you take physics. We're not going to really deal with this one in chemistry very much. But 1 Newton is kilogram meter per second squared. So this is the SI unit for force based on kilograms and meters per second. So that's a Pascal, but it's not a particularly convenient unit of pressure because it's a very small unit of pressure. So the more common way that we do it in chemistry especially is using what's called atmospheres. So this was the unit of pressure we used in Chapter 7 when we were calculating expansion work. Atmospheres is the most common one. And basically it's, 1 atmosphere is equal to the average atmospheric pressure at sea level. And then there's some relationships here. So 1 atmosphere in terms of pascals is 101.3 kilopascals, which is 1.013 times 10 to the 5th pascal. So pascal, as I said, is a tiny unit of pressure, so it's not particularly convenient. And then there's a unit of pressure that has also been invented to make it more relevant to SI units, which is called a bar, 1.013 bar. All right, so if we take basically divide this by 10 to the 5th, we have a new pressure unit called bar, which is very similar to an atmosphere, but it's based on SI units. So that's some things you might see here and there. But the important one that's going to be coming up all the time in this course is what's called torr, which is the full name for that is Torricelli, named after, as you might guess, an Italian guy. So 1 torr is equal to 1 millimeter of mercury. So when we measure the pressure with a mercury manometer or barometer, that unit of 1 millimeter of mercury is also called a Torricelli, and these two are going to be used interchangeably. So they're equivalent to each other, and you'll see both of them. But then the key conversion factor, the one that you'll definitely have to know, the rest of these will, if you need them, we'll give them to you. But the one that you should definitely become familiar with is that 760 torr is equal to 1 atmosphere. All right, so as I mentioned in the last slide, the typical atmospheric pressure at sea level is 760 millimeters of mercury, which is equivalent to 760 torr, and then we call that 1 atmosphere. So these are the two pressure units that we'll use all the time in most of the homework problems and most of the example problems that I do throughout this section. All right, so those are our pressure units, and then because we have all these different conversions, we should know how to convert them, and we're pretty good at converting units by now because we've done it a lot. So let's say we have a compressed gas cylinder, like a helium one that you would use to blow up balloons, and those are typically supplied at a pressure of 2,000 psi. So psi is another pressure unit. It's a non-standard one based on English units, pounds per square inch. But here we're giving you the conversion. We want to know what is the pressure in millimeters of mercury. So 1 atmosphere is about 15 psi, 14.7 exactly. And then we also have that other conversion that you should know. 1 atmosphere is 760 torr. All right, so if we just want to do the conversion, it's going to be a two-step conversion. If we're looking for the pressure in millimeters of mercury, it's going to be, we have 2,000 psi. The first conversion we have involving psi gets us to atmospheres, so there's 1 atmosphere in 14.7 psi. And then we also know the conversion from atmosphere to torr is 760 torr per 1 atmosphere. And then finally, we know that 1 millimeter of mercury equals 1 torr. So if we really want to record it in millimeters of mercury, we can do that trivial conversion. So what we get is 1.03 times 10 to the 5th millimeters of mercury, which is around 100 meters of mercury. Now, this was a pretty simple exercise of unit conversions that we're going to have to do a lot in this section, converting between different units of pressure. However, what it also should tell us is that 2,000 psi is it's a pretty high pressure, but one that we can readily obtain inside of a compressed gas cylinder, and that would require a mercury column that's 100 meters tall to measure it. So for really high pressures, we're not going to use things like mercury manometers. The mercury barometers, mercury manometers that I introduced on the the very beginning, those are good for relatively low values of pressure. But anything that's really high, like a compressed gas cylinder, 2,000 psi or so, it's just not practical. So we have other, obviously more sophisticated devices for measuring pressure for those types of things. All right, but let's get into now what are called the gas laws. So when early chemists were studying gases, they wanted to understand their behaviors a little bit, so they measured different things about them. And the easiest thing to change or measure for a sample of gas is the volume, right? We can have a movable cylinder here, for example, where we can compress that or expand it, and then we can measure what happens to the gas on the inside as we do this. So all the gas laws are derived relative to volume of gas, because volume is one of the simplest things to measure for a sample of gas. So the first thing we're going to talk about is what's called Boyles Law. So we're going to watch a quick video that shows an experiment. And what they're going to be doing in this case is varying the pressure of the gas and seeing what happens to the volume as they do that. Okay, so the setup here is that, is this going to go? All right. So he has a balloon inside of a vacuum chamber. So he's going to evacuate the chamber, which is going to reduce the pressure inside. And we can see that as he does that, the gas inside the balloon expands. Okay, so the balloon is filled with gas and he's evacuating it. It's getting bigger and bigger and bigger as the pressure inside the chamber gets smaller and smaller. Okay, so this little vacuum, this little tube here is connected to a vacuum. So eventually it fills the container, and then if he lets air back into the chamber, it raises the pressure back up. We see that the volume of the balloon goes back down. He can do the same thing with a marshmallow peep. So Easter is just around the corner, so this is pretty timely. So he's going to lower the pressure inside, and there's going to be the gas that's trapped inside of the marshmallow, and you can see the peep grows in size as the pressure decreases inside of there, and then when he lets the gas back in, it goes back down and loses a bit of its structural integrity in the process. All right, and then finally, this one here is shaving cream. So again, there's gas trapped inside the shaving cream. As he lowers the pressure inside the chamber, the shaving cream expands because the gas that's inside of it starts expanding as well. And then now he has a huge mess on his hands. I don't know if this one comes back or not. Okay, so that's what happens when we change the pressure of a sample of gas, and that's sort of the effect on the volume. All right, so what we saw in that demonstration was that the volume was inversely proportional to the pressure. So we write that as V is proportional to 1 over the pressure. So what that means is as the pressure went down, the volume went up. As the pressure went up, the volume went down. They're inversely related to each other. And so that's how we say that in words. V is inversely proportional to P. And a math trick that we've seen many times when deriving equations, and we'll see it a lot in this section too, is that if you have a proportionality, the way that you make it an equality is just to put a constant on one side. So if we say that, we can say that V is equal to some constant K divided by P, although this constant is ill-defined, as we'll see. But what we can then do is rearrange this and say that PV equals K. So the product of pressure times volume is always going to be constant for a sample of gas. And then we can then say that the P1V1, the pressure times the volume of some initial set of conditions, is going to be equal to P2V2, the pressure times the volume for whatever the final set of conditions are. So this is called Boyles Law, which is the relationship between pressure and volume for a sample of gas. And they're inversely related, so the product of the two is going to always be equal to some constant. We can set them equal to each other. for some initial and final set of conditions. Okay, so we can do a sample problem with Boyles Law. Let's say we fill a balloon to a volume of 0.500 liters at sea level, and then we let the balloon rise to an altitude of 6.5 kilometers where the air pressure is 0.4 atmospheres. So remember, as you go up in the atmosphere, the pressure decreases. We want to know what's the final volume of the balloon going to be. So we're going to just assume the temperature is the same in all cases. So in this case, all that's changing is pressure and volume. We know that the initial volume, V1, is 0.5 liters. The initial pressure was not given to us, but if we're at sea level, what's the pressure going to be, or at least approximately equal to? 1 atmosphere. All right, so that's a little thing you might see in some of these problems. If we're telling you you're at sea level, that means the pressure is 1 atmosphere. The altitude doesn't matter because all that matters is pressure and volume. And we know then when it goes up to 6.5 kilometers, that's going to be our P2. So all we're doing here is solving for the final volume V2. So P1 V1 equals P2 V2. V2 is equal to P1 V1 over P2. And then we just plug in. And again, because there's a ratio of P1 to P2, it doesn't really matter what units we put in for the pressure as long as the two are the same. So we're given the units in atmospheres, so we should just go ahead and use that. But we have 1 atmosphere is P1, the initial volume is 0.5 liters. And then the final pressure when it raises up to the sky is 0.400 atmospheres. So both units of pressure in atmospheres, they cancel out, and that'll give us a volume that's also in liters, 1.25. All right, so as the equation implies, if the pressure decreases, the volume should increase, and the volume goes from 0.5 liters to 1.25 liters. So that's an example of Boyles Law, which is the relationship between pressure and volume. Now there are other relationships involving the volume of gas that we can derive as well. So the next one is Charles' law, which applies to fixed pressure in a closed container. So if we keep the pressure constant, but instead we're going to change the temperature of the sample, what happens? How does the temperature and the volume relate to each other? All right, so we have another demonstration of this. Very simple experiment here. So this person here decides that gloves are optional when working with liquid nitrogen. I wouldn't suggest that myself. So he has a balloon, he's cooling it down in liquid nitrogen, making it really cold, and we can see that as he does that, the balloon shrinks. So as the temperature goes down, the volume of the balloon gets smaller. And so he's going to completely submerge it, and you can see that it collapses to almost nothing. He's going to take it out, and using the highly scientific process of blowing, he's going to warm it back up. And you can see that as the balloon warms back up, as the temperature goes up, the volume goes back up to what it started as. So there's a direct relationship between volume and temperature, where if the temperature goes down, the volume goes down. If the temperature goes up, the volume goes up. So we write that as volume is proportional to temperature, which means that V is directly proportional to T. All right, and so then what we can say then is volume is equal to some constant, which I'll call K prime to distinguish it from the last one, times the temperature. We can rewrite the equation as we did before and say that V1 over T1, so we put everything that's constant on one side, and we can say V1 over T1 equals V2 over T2. So this is an equation that represents what's called Charles's law, which is the relationship between volume and temperature. In this case, and in every other case that's going to involve temperature, the units do matter. So for temperature only, you have to use a certain set of units, which is Kelvin. All right, so this is the first time where the temperature units that we're using matter for us. And the reason is because Kelvin is what's called the absolute temperature, and the volume is not going to be proportional to the temperature unless it's in those exact units. If you're talking about Celsius degrees or any other measure of temperature, then the volume is not going to be proportional to that. So only if the temperature is in Kelvin is this equation going to work. And as a reminder, the temperature in Kelvin is going to be the temperature in Celsius degrees plus 273.15. If you left the 0.15 off, it's not going to really matter. But it's temperature in Celsius plus 273 to get into Kelvin. So any type of gas law problem that we're doing, this is Charles's law. We're going to see other types of equations and things that involve temperature. For any of those, you have to use the temperature in Kelvin. So I'm going to start drilling that point home now. All right, so let's do an example of Charles's law. So let's say we have a sample of gas that has a volume of 79.5 milliliters and the temperature is 45 degrees Celsius. And we want to know what volume would that occupy at 0 degrees Celsius if the pressure were held constant. Okay, so we're relating volume and temperature, so this is called Charles's law. And they're directly related, so it's going to be V1 over T1 equals V2 over T2. If we look at the problem, the initial volume is given to us, the initial temperature is given to us, in Celsius anyway, and then the final temperature is given to us as well. So we're solving for the final volume V2, which is going to be V1 times T2 over T1. All right, so the volume, we can use whatever unit we want. There's no restriction on volume units for this. 79.5 milliliters is given to us. But remember, the temperatures have to be in Kelvin, because if we were to put this 0 degrees Celsius right in, that would say the final volume is 0, which is sort of a nonsensical answer. So we have to convert both temperatures into Kelvin. So the initial temperature is 45 degrees Celsius. If we add 273 to that, we get 318 Kelvin. And then the final temperature, which is 0 degrees Celsius, we add 273 to that and get 273 Kelvin. All right, so those are the temperatures that we have to use. We put T2 in the numerator for this one, which is 273. T1 in the denominator, 318 Kelvin. And so what we see is that when we calculate this out, the volume shrinks to 68.2 milliliters. Okay? So even though this seems like a pretty big decrease in temperature, 45 degrees Celsius, if you're not that familiar with the Celsius scale, I mean, 45 degrees is probably hotter than any shower you've ever taken, and 0 degrees is the freezing point of water. That seems like a big difference, but the volume is only changing by a small factor here because it depends on the absolute temperature, not the temperature in degrees Celsius. Okay, so that's Charles's law. And then finally, the last one we'll talk about individually is what's called Avogadro's law. We introduced this very briefly early on in the course. This is one of the early key observations of chemistry, which is called Avogadro's law. Avogadro has a number named after him, but this is actually what he really did, this contribution. And this one I don't have a video for, but this one I think is the most explanatory of them all. Okay, so let's say we have a balloon with 1 mole of oxygen in it. That would be a pretty big balloon as it turns out, but let's just assume that's the case. And then we wanted to add another mole of oxygen to that, so we have 2 total moles. Do we think the balloon's going to get bigger or smaller? If you add more gas to a balloon, does it get bigger or smaller? Bigger. That one's pretty obvious from our everyday life. If you've ever blown up a balloon. If you haven't, then I'm sorry that you had such a terrible childhood. So n is number of moles. And so we can write that the volume is proportional to the number of moles. V is proportional to n. And then the same tricks as before. We can set that equal to each other by putting a constant in there, which are called K double prime, just to distinguish it from the rest, because they're not all the same. But the real form of the equation that we're going to use is we're going to move everything that's not constant over to one side and set the initial and final equal to each other. So V1 over N1 equals V2 over N2. So this is an equation related to Avogadro's law. So we can use it then, of course, in certain types of problems where, let's say, we have at a certain temperature and pressure, we have 28 grams of nitrogen occupying a volume of 20.8 liters, and we want to know what volume does 40 grams of oxygen occupy at the same temperature and pressure. So this one looks a little bit weird because we're talking about masses of gases now, but remember that Avogadro's law deals with moles. V1 over N1 equals V2 over N2. And what we're looking for here is the volume of the oxygen sample. So this is going to be our, let's call this V1. We're looking for V2, so we're going to solve for that. V2 is equal to V1 times N2 over N1. All right, so we have the volume of one gas sample that we're comparing here, but we needed to find the number of moles. So N1 is going to be the volume. So remember, V1 is the volume of the nitrogen sample that we're given. So N1 is going to be the number of moles of nitrogen that are in that sample. And an old trick that we've seen for a while now is taking masses and converting into moles. So if we have 28 grams of N2, we're told in the problem that the molar mass is 28. So if we divide that by the molar mass, then we get 1 mole of N2. So we have 1 mole of N2 in this sample that occupies 20.8 liters. So that's our N1. And then for N2, which is the moles of O2, we want to figure out how much volume does that sample occupy under the same conditions. N2 is the moles of O2, which is going to be given to us by taking the mass of O2 and then dividing by the molar mass of O2, which is 32. And that comes out to 1.25 moles of O2. So we put 1.25 moles as N2 in the numerator, 1 mole as N1 in the denominator. Moles cancel out, and we find that the volume of this sample, which is 1.25 moles, is 26.0 liters. All right. So this introduces an important point for us, which, as we said in Chapter 5 and Chapter 6, when we're doing stoichiometry, moles is the key quantity for us, and that's going to be true for gas laws too. So the properties of a gas are going to be related to the number of moles of gas, not just to the mass of the gas. So anytime we're doing these, we have to take masses and convert into moles like we did here. So now we have all of these individual gas laws, and you might be starting to think, well, that's already 3 equations I have to memorize, and what about the relationship between moles and pressure, and what about the relationship between volume and temperature, and all those other ones that we could have, other combinations, because we have 3 variables now: pressure, volume, number of moles. 4. Pressure, volume, number of moles, and temperature. We have, how many different equations can we write with those 4 variables? That's a lot. So what we're going to do now is derive one single equation, which is going to be the only equation you ever have to remember for gases. So it's important from a conceptual standpoint to know the difference between Boyles Law, which is volume and pressure, Charles' Law, which is volume and temperature, and Avogadro's Law, which is volume and number of moles. You might see some conceptual problems related to that. But for the standpoint of equations, for doing the problems like we've been doing today, really you don't need all of these separate equations. It's kind of foolish to try to remember all of them. Let's just derive a combined equation using all of them. Okay, so let's put it all together in what's called the ideal gas law. Okay, so we saw from what we've introduced so far that we have Boyles Law, which is that the volume is inversely proportional to the pressure. So all of these equations and all these proportionalities that we talked about involve volume. So we're going to write them all in that form. We have Charles's law. Volume is proportional to temperature. And then finally, Avogadro's law. Volume is proportional to the number of moles. All right, so this is another math trick. We saw it when we were introducing the equation for heat, Q equals mc delta T. If you have something that's proportional to 2 or more different things, it is also proportional to the product of those 2 or more different things. So we can combine all of these into one proportionality by taking the product. Let me erase my sad attempt at a bracket and just make it simpler. All right, so if we want to find one equation or one proportionality that's related to all of these, we can take the product of these 3 things. So volume is proportional to all 3 of these things individually. Volume will also be proportional to the product of those 3. So we can write that volume is proportional to 1 over the pressure times the temperature times the number of moles. Okay, that's a common math trick. Or we can also write this if you put all the, if we want to make it a little bit simpler, pressure times the volume is proportional to the number of moles times the temperature. So we just move the pressure over to this side, we just multiply both sides by the pressure. And that gets rid of this fraction here. Now we have PV is proportional to NT. And just like any other equation, if we want to take this equation and make it into an equality, so we're going to take this proportionality and make it into an equation, we just have to put a constant on one side. And for whatever reason, the powers that be decided to put the constant on this side of the equation, and that gives us what we are maybe already familiar with, PV equals nRT. And they call the constant R in this case, not anything else. So R has a very specific value. It's 0.0821 liter atmospheres per K mole. This value of R is what's called the universal gas constant, and it's on your periodic table, so you don't have to memorize it. But it's one we're going to use a lot, so you probably will, even if you don't try to. So it's the universal gas constant, 0.0821. And so this whole equation here tells us everything we'd ever want to know about a gas. It relates all four of the important variables: pressure, volume, number of moles, and temperature. They're all related to each other. And so we call this an equation of state because it tells us everything we'd ever want to know about a sample of gas. All right, so we now have sort of seen this equation. It's probably one you've learned if you've taken any other chemistry course before. This is where it comes from, and then next time we're going to see a lot of different ways to use it. But before I let you guys go, let's have a bonus quiz because it's about that time. In honor of baseball season, we'll have a bonus quiz today, so get out your clickers if you have them and get situated for a quiz. So let's get this pulled up here. Let's see. What do I do? All right, polling is open. I'll start the timer here in a second. All right, so this question is, if the enthalpy of formation for methane is minus 75 kilojoules per mole, what is the enthalpy change when 2 moles of CH4 are decomposed into carbon and hydrogen? So polling is open right now, and I'll go ahead and start the time. So I'll give you 2 minutes. There should be plenty of time for this one. Math's not too difficult. I'll show you real quick. So we're talking about, we have CH4, sorry, we're talking about the enthalpy of formation for CH4. So that's going to be given by this equation here. And the enthalpy of formation is minus 75 kilojoules per mole. And then what I asked you about was the enthalpy change for this reaction, which is taking 2 CH4s and decomposing it into carbon and hydrogen. So what we're doing here is we're taking the formation equation and we're flipping it and doubling it. So the delta H for this is going to be minus 2 times the delta H of formation. So remember, if we flip an equation, we change the sign. If we change the coefficients, we change the delta H by that same amount. So overall, that gets us to 150 kilojoules. All right, so that's how we do that one. I guess we'll get out a little bit early today, which I'm sure you don't mind, and I'll see you on Monday.